Okay, so I think the Suvrat and Onkar asked me to talk about localization in quantum gravity. That subject is a little bit above my pay grade. So what I'm going to do is start with local observables in quantum field theory in Minkowski spacetime, and we will look at free scalar field theory to begin with today. And the reason is that there are two properties that we would like to understand properly. One is what is called a Riesz-Leader theorem, and the other, which is going to be very important when we go to gravitational observable, which is called a split property. And then after that, we will focus on understanding existence of observables in gravity, and then situation becomes very nuanced and complicated in some sense, because then you could have different asymptotics depending on ADS, asymptotically flat or even de Sitter. And there are, as we will see, maybe if not today, then next lecture, there are different kinds of observables. There are the simplest ones we can define, which are called boundary observables. But then there are these singular observables, which are called rest, where you kind of fix a coordinate system in the bulk with respect to the boundary metric. And then there are these interesting, seemingly local observables called relational observables. And the idea is to see that, if in gravitational theories, can we prepare subsystems in the bulk, and if not, why not? So that's the goal. And of course, even here, gravity, there'll be, as we will see, nuances depending on whether we do perturbation theory, which is where already these questions are hard and to some extent not completely settled, or if we are in a completely non-perturbative regime like string theory. Okay, so I'm going to start with a very simple example first to understand what really we mean by local observables in quantum field theory. So we are going to start with like a simplest example, which is free scalar field theory. And I mean, this is something everyone in this room know, but we are going to look at this theory, quantum field theory, even though it's trivial, a bit differently to bring out certain nuances in localization of observables in quantum field theory. So let's just start with the following algebra of operators. So I'm going to introduce a notation first, and then I'm going to motivate what this algebra is. So this algebra of operators is going to be an algebra of operators defined on the full manifold M, and I'm going to always denote the algebra as A of M. And this algebra is defined by following generators and relations. So so these are abstract elements which are labeled by functions of compact support and smooth functions in M, and they satisfy following properties. So this is a definition of our algebra. So most of these will be completely obvious to you. Why are these the defining equations for this algebra of free field theory? Where this G is defined as the retarded minus the advanced Green function smeared with these functions of compact support. So G plus or minus Fg is simply integral Fx G plus minus xy gy, and where these are retarded and advanced Green functions respectively. So you can immediately convince yourself that if you take F to be basically mode functions, then this will reduce for you the usual canonical commutation relation of a free field. And of course, even if you, I mean, this is not even that fancy. I mean, if you look at Coleman's lecture notes in quantum field theory, this is the defining relations for free field theory that he starts with. So now this is the algebra which is generated by the following relations. And this algebra is actually, we can quantify this algebra very nicely. And so this algebra has the following property. So let me first define the properties of this algebra. One is that if you see that if F and G are in causal complements of each other, then I mean, they are supported in causal complements of each other, then phi F, phi G is obviously 0. And that's one property which is called causality, of course, or sometimes called Einstein causality. And then this we can use these generators to define the algebra. So let me define the algebra now. And the algebra is going to be simply identity, which is an abstract element. So one thing to notice is that this complex numbers times identity. One thing to notice is that this identity is not directly included in this class of functions because these functions are only compactly supported. So there is no constant function which is which is allowed here. So this identity is something which is additional in our algebra. And then of course then we take symmetric tensor products of our elements, and then so I'm going to write something and explain what I mean. Where maybe I put project P here, where we are taking all functions which are smooth and have compact support and quotienting by functions which satisfy the equations of motion, which is box plus m square f equal to 0. So the algebra, the algebra that we are starting with of linear operators is isomorphic to all functions which have compact support, quotiented by this condition that box plus m square f equal to 0. So this quotienting is what I am defining here. So this quotient algebra is the basic algebra, and then symmetric tensor product from here gives us the algebra of the full algebra of observables for the free field. Yeah, sorry, I should. It's of compact support. Yeah. So phi, actually, the way we are doing it here is that there is no phi to begin with. So it's important to not think of this as integral phi x fx as we do. I mean, we could do that. So these are just algebras which are labeled by, each element is labeled by a function, and they satisfy this constraining relation. So that's isomorphic to algebra of functions of compact support, quotiented by all the functions that satisfy equations of motion. So as an algebra, it's the same. Sorry, yeah. The P is basically it's the kernel of, so P is, box plus m square is P. So it's a kernel of, it's kernel of P rather, if I do it like that. Okay, maybe I write it as kernel of P, where P is just this operator. No, we can, but we don't need to, because if we do usual quantum field theory, then we start with like wave packets, which are just smooth functions, or the localized wave packets, which are smooth functions. So it's completely sufficient to start with smooth functions, right? I mean, this is just ordinary field theory, but just written in a way that, as you will see, bring out some qualities of the properties of general quantum field theories. Any other?
So
yeah.
It's a Lie algebra. What kind of algebra is it?
So it's actually universal enveloping algebra because you are quotienting by the commutator relations, but I didn't go into that. Yeah. So it's really like you look at all products and you identify the commutator with identity.
Oh, so it's not a Lie algebra. So you can multiply these.
Yeah, exactly. So say that again. This one? No, phi f. Think of phi f as an element of the algebra. Okay, so don't think of phi f as phi x fx. Just think of it as an element of the algebra. Yeah, is that? Yeah, that we don't want to use it simply because it's not needed at this level, and that's really a little bit, if you think about it, it's a bit complicated because phi x is really not an operator. It's very singular. So it's not incorrect to do, but you will see that we don't need it. So at the level of where we want to go, it's enough to really think of this algebra as being generated by smooth functions of compact support, quotiented by this kernel of this, wave operator P. Okay, so that's, sorry, there was a.
And you will also impose this condition.
Yeah, exactly. Yeah. Yeah, so this is symmetric tensor product. I was just not being very detailed. You are right that we basically say that wherever we see a commutator, we quotient by this commutator. Yeah, I just didn't write it. Yeah, sorry. Yeah. Also, at this stage, just quotienting by kernel of the wave operator. So this P is just this operator box plus m square. No. So we start with that sort. So we can have any function, right? Doesn't satisfy anything. Yeah. But now I want to look at the quantum fields which satisfy equations of motion, which is same as looking at functions which satisfy this. Yeah, but then you may have to put boundary conditions, certainly, right? I mean, you want compact support in 1/2 or something, but then at the boundary, you'll have to put some boundary conditions, right? No, I mean boundary at the x equal to 0 or, at the codimension 1 hypersurface, right? No, infinity, there's no problem because these functions are compactly supported. So here there is infinity also, right? This is Minkowski space. So that is exactly what we take care of by compact support, right? So that's not an issue at all. In fact, if you think about it a little bit, this kernel of the wave operator is same as image of this G, which is because G is G plus minus G plus minus G minus. It's retarded minus advanced, so it really satisfies box plus m square of G plus minus G minus equal to 0, right? Because both of them gives delta function. So it's not important for us, but you can immediately check that this algebra is basically same as the algebra which is which is in the image of G. I'm only writing this part, and so what is an image of G? So by image of G, we simply mean that if I start with the function of compact support, and then I take the retarded minus advanced, and pictorially we can see what this is doing, right? Because it's taking a function and the retarded propagator is going to move forward. So suppose your function had compact support like this, your f. Suppose this was support of f. And then if you do retarded propagation, it's going to give you some propagation inside the light cone, and the advanced is going to give you the propagation here. So the image is all the functions which have only spatially compact support, because now the image is not compactly supported, right? So this image of G is all the functions which are smooth and spatially compactly supported on the Minkowski space. So that's it. So that's that's the generator. So it's very explicit. We can simply label the elements of the generators as all the smooth functions which are spatially compactly supported. Okay, so this is what is called the global algebra of a free quantum field theory on a flat space. And you may be annoyed why we are doing all these things, but what it buys us is the following, because from here we can build local observables. So now consider.
I'm still confused about the phi.
Yeah.
Operator. What precisely is assumed? Is it, for example, a bounded operator?
No. It's not bounded. I mean, it's just any function. Yeah. It's just this. Yeah.
No, finish.
No. It's just that just think of the algebra as algebra of smooth functions with spatially compact support. Those are the generators. Then we have to quotient by this relation, and that's it. That's the algebra, full algebra. That's this algebra.
Okay, in this relation, the right-hand side is a function. It's not an operator, right?
Yeah, exactly. I mean, sorry, it's your identity. I apologize. I mean, of course, identity.
But those things are not in your algebra. You only have you have identity.
Yeah.
Times a complex number, but that's a constant.
Yeah.
In space. And then those things are all everything after that is operators, right? So you have C number functions.
Yeah, it's a symmetric tensor product, exactly. It's a symmetric tensor product of your generators such that wherever you have a commutator, you use this relation to reduce the commutator to the identity. So you start with like phi f, if you have phi f tensored phi g, you write it as phi f tensored phi g plus phi g tensored phi f plus the commutator, which is the identity operator then. So you keep doing this reduction. Is that, I just, no, yeah. The Green's function itself is not smooth, but when we smear it with smooth functions of compact support, it's perfectly well defined. It's like a convergent integral.
It's still not compactly supported, or it is compactly.
Well, no. If I,
That's a number. Oh,
yeah. It's a convergent integral with a number.
Okay, sorry.
Yeah.
This capital G of little f little g, that's a number.
Number, it's a number.
That's not a function.
Yeah, for EV, F, and G, it's a number. Yeah, thanks. Yeah, M is full Minkowski. It's just full Minkowski. It's just algebra of free scalar fields on Minkowski space with mass M. That's it. But what it buys us is something interesting, which is that we can define now local observables. So
You are using the symmetrized product because of the symmetry.
exactly. So every time you, yeah, every antisymmetric combination is identity, proportional to identity. Yeah. So we can define, so consider, so now we are going to do the following thing. We are going to first cover M with, this is, I'm going to write it a little formally, with union of what we call, so I'm going to index it with some alpha, where each O alpha is a causally, I will explain what this means, causally convex open set. What we mean by this is that it's a set which is such that if you take any 2 points in the set, so it's some set, sorry, I don't know, I cannot write there, I guess, so what's the, oh, I can write up to there, okay. So by causally convex open set, I simply mean any set which is such that if you take any 2 points in this set, then any causal curve between these 2 points also lies inside this set. Okay, that's what we mean by a causally convex open set, and you can show that, I mean, it's known that any globally hyperbolic spacetime, and including Minkowski, can always be covered by open sets which are always causally convex. A standard example of causally convex open set is a cone. But this is not a unique example, but this is one example of causally convex open set which is often used in formulating algebraic quantum field theory. So the idea is that you take some compact spatially compact slice, and then just look at this cone. And so this is one example of O. Then obviously you can check that every causal curve which lies inside this will always pass through this, will always completely belong to this causally convex open set.
What's not an example of this?
Oh, great, yeah. That, I mean, you can, for example, look at take a slice. Is not an example because take a point here, and you can draw a curve, which is intuitively what is not convex is not, okay, that's not true, but I mean, pictorially. Yeah. Well, I mean, usually when we cover manifolds with chart, we start with open sets, right? Like, we are just putting a topology with specific open sets. So we are just choosing specific type of open sets, which are these ones. Okay, so I will erase. But what this does for us is give us algebra of local operators now, and that's interesting in its own right. Now we are putting in additional structure, exactly. So we are now saying that, which is in free field theory trivial, but we can generalize it in a minute. So we say that, okay, so I'm now going to define for any causally convex open set, we look at the algebra of operators, which are basically phi f, where f is smooth, compactly supported inside O. That's it. So it's generated by these guys. So now, so that's for any O we can do this. And now you notice immediately that some consequence is obvious. One is that, so by the way, first of all, I can, this one in itself naively will not have a unit because it's only generated by these guys. But so we have to add a unit as again an additional element. So the full AO is the same unit that we used for the full algebra AM plus, I hope what I mean. Let me call this A tilde O plus algebra generated by A tilde O. Okay, so I add a unit, again the same unit operator, identity operator, and then the functions which are compactly supported and smooth, and they are inside O. Now you notice that if some consequence become obvious, one that if O1 is contained inside O2, then the algebra AO1 is the sub-algebra of AO2. And this property is sometimes called isotony. Okay, it's a trivial statement for free field theory, but it just follows, right? Because you take functions which are supported inside some O1, you multiply them, and that will always be a function supported inside O1. So that is obviously part of the algebra of functions inside O2 if O2 is larger, contains O1. Second interesting property, which is again causality, which is that this algebra, local algebras commute if restricted to O. So you cover a manifold with this causally convex open sets, and now to just look at functions which are smooth and they are supported inside O. Okay, so all those functions is going to generate A tilde O, and it's just a technicality. AO is we have to add a unit. So it's okay, and then the this will be true if O1 is in causal complement of O2, and I will always denote causal complement as is standard with a prime. This simply comes from the fact that if you just evaluate the Green's function, that will be 0 if O1 and O2 are space-like separated, right? So that's what this thing means. So one thing this causally convex open set biphoresis give us, we can directly implement ideas of causality by simply saying that two sets will be causally separated if O1 is in the causal complement of O2. So this is causality. And finally, can I write here, Suvrat, or no? Oh, okay. Finally, the third one is that, of course, if you look at, oh, okay, yeah, that's what I was asking. Okay, I will write it here then. So there are two more conditions that kind of, one of them follow immediately, the other one is slightly subtle that I just explain in a minute. So the third condition, which is kind of obvious, is that if phi f belongs to AO, then phi f star, of course, also belongs to AO. Because phi f star is phi of f star, and if f is in supported in some open set, then its conjugate is also supported in the open set. So this endos AO with what is called a unital star algebra. So once again, as he was asking, this is an algebra where you take the tensor product of generators and you quotient by the commutator. So that's the symmetric tensor product. It's also called the universal enveloping algebra. And so that's for each O. For each open set, we have a unital star algebra like this. And notice an interesting fact which comes out, at least for this trivial theory, which is called the time slice axiom. A time slice property in this case, because not an axiom for this theory, which is the following. If O1 is contained inside O2, but O1 contains at least one Cauchy slice of O2, then AO1 is equal to AO2. And this is because, of course, the fact that all the solution to equations of motion inside O2 are completely determined by the Cauchy data, which is on a Cauchy slice in O2. So if you give me an O1 maybe as a whole subset of O2, but if it contains at least one Cauchy slice, then the algebra will be completely isomorphic. And so this property, which in general is hard to prove, but for free field theory, it's just obvious by inspection because of the property of equations of motion, because there are hyperbolic equations. So this is what is called time slice property, or in general, as we will see, time slice axiom. And finally,
hello. Can I ask a question?
Yeah.
So usually when we do QFT, like the boundary conditions change the Hilbert space and so on, right? But here, whatever you're saying, because you use compact functions.
Yeah.
Why is that the?
Yeah. This is just, if you want to compute excite normalizable states, then we will obviously smear our, if you want to go with the usual QFT picture, smear field operators with wave packets, right? So that's all we are doing. There is no boundary because we are in Minkowski space. Right? Maybe I misunderstood. So the whole space-time is M. And now we are saying that this full algebra of all operators is this algebra which can be obtained by looking at algebras inside each open set. And I'm just choosing for convenience, as you will see, these open sets which have these nice causal properties.
There's no sense I can change the Hilbert space by changing boundary conditions or something.
Right now there's no Hilbert space at all because we have algebra. I haven't quantized it yet.
Change the algebra by changing the Hilbert space.
Well, here I don't see immediately how, because we have a non-compact Minkowski, but of course, as someone was asking, if you have some half space or something, then there'll be additional structures we have to put, right?
Usually in gravity and so on, people worry about H modes and things like that.
Oh yeah, absolutely. So we will come to all that. I mean, this is really a dumbest possible example. I can see, this is a silly example, right? It's free scalar field theory. And so the whole idea is that we are going to abstract out some properties of quantum field theory in Minkowski from here, and then going to see how many of those properties can be applied to quantum field theories in couch spacetime or quantum field theories with dynamic gravity. So that's the sort of the overall logic. That's an excellent question. It's just that we are right now working with such a silly example that it doesn't have that structure that you're talking about.
Even if you're just doing Chern-Simons in 3D space or something, like just...
Yeah, of course. Even here, if you had massless fields, you could have modes at null infinity, etc. But even we are even avoiding that because we have a mass gap. So we really have a very theories with no infrared properties, non-trivial infrared properties. So it's I think that was your question, right? That was a definition of the O, like that's the definition of O. So convexity is important because of the sub-isotony. So the fact that you want, if your O1 is inside O2 and you want the algebra to be the sub-algebra, that's where the convexity enters. I mean, we can talk more about it, but you can take this as one possible chart, right?
No, but I think it's in the
G, it's because of G also, yeah, thanks, yeah, because of the fact that G will ensure that, thank you, yes, you're right. So if your phi f is in some O1 and phi g is in O2 and O1 and O2 are causally separated, then they commute. It naturally follows from the fact that O1 and O2 are causally convex open sets.
But that's about
Space like separation of sets, not slice, right?
but that's only what is causal part of the
No. It's just that I think without it will be hard. I have to think about this. It's a good point. So you are saying if I wanted to work with these kind of things. Yeah. That's another thing, right? Because it's not causal. I mean, this, the data. If you give data here, the solution will not be restricted to this, right? It will leak out. That's exactly what he's saying. Thank you. Yeah. So we just want, yeah, exactly, because these are on-shell solutions, right? So. Okay, so yeah, and finally one obvious property, because we are in Minkowski space, is space-time covariance. So if G is the element of our group, Poincare group, then we see that we can define, and if phi f belong to AO, then phi g dot f belongs to a g dot o. So as a whole, the union of all these algebras which are local, they obviously have a nice covariance with respect to Poincare transformations. So basically what we have done through this complicated sounding procedure is to split the full algebra into, this is again schematic, into the algebra of local operators. And now we can abstract out the main properties that we found, and these are the axioms of quantum field theory in Minkowski spacetime, and the axioms are that, so these are the axioms. So I'm going to write the axioms. Is there any question about what properties we have found here? Or? Okay.
So that holds for any cover, like causally convex subsets.
Yes. Yeah, exactly. And so now the axioms can be formulated like this.
That union is an algebra, like it's generated by that union. It's not equal to the union.
No, I mean schematic, you are right. So one is to, yeah, to be a little more careful with the exact definition. Basically the point is that all I want to say is that any element of this full algebra can be obtained from, as a linear combination of elements of the algebra here. This product is already there in AO. Yeah, sorry, also product. So this, yeah, maybe you should, I should, it's a bit complicated because any operator here is on a function of compact support. So I can always find an O in which, yeah, but it will always, I think we can make it more rigorous, but you see what I'm saying, right? Like you take product of two operators, which is also, then we can find a bigger set in which it's supported, and so then it's part of that AO. So that's why this union is a bit complex. It's not some trivial thing, right? Yeah, exactly. Because
I think I'm missing something fundamental. I mean, we're somehow fixing the set of O's. It's not all causally convex O's. I mean, if it was all causally convex O's, it would be trivial. Just choose M to be one of your O's.
Yeah.
This is a trivial statement.
Yeah.
So I thought the point was that
exactly.
I can choose a set of O's which is not.
Yeah, it's a chart, absolutely. So this is subtle. I completely agree with you. We have to make it more rigorous, but it's just that's why I put an arrow to indicate that we can generate the algebra from here. Yeah. No, O's don't obey. I mean, right now all we saw is that if your O1 is a subset of O2, then the algebra AO1 clearly is a sub-algebra of AO2. But the point is that they can be equal as algebras if O1 contains at least one Cauchy slice of O2. That's the point. So this is, even if O1 is a proper subset of O2, it does not always mean that AO1 is a strict sub-algebra of AO2. They can be equal if O1 contains at least one Cauchy slice of O2. That's the time slice property. No, it's exactly. So O is a chart for M, na? Like it's open sets which is covering M. And as he said that this, that's why I'm not writing any equality, because I just want to indicate that this local algebra generate the full algebra.
So we have to take the union over the entire chart over M.
Yeah. You fix the chart where every element of the chart is a causally convex open set. It has to cover M. That gives you AO. And then the point is that looking at products or sums of elements in AO, I can generate any element in AM.
Hi, Alok. I'm a bit puzzled about the second axiom that you wrote, which said something about the commutation of two algebras, AO1 and AO2.
Yeah.
When O1 belonged to the complement of O2. Was that the case?
Yeah, if O1 and O2 are space-like separated, which would mean that O2 is in the causal complement of O1, then of course they will commute, the algebras will commute. Okay, so now we can axiomatize this thing for any quantum field theory on flat spacetime, not free field theory. So these are, I think these are called Kastler axioms. which can be because for QFT in Minkowski spacetime. So I'm not doing full justice to these axioms because these are really these have been generalized to globally hyperbolic spacetime. But for the purpose of this, at least today's lecture, I will stick to just Minkowski spacetime. So then the axioms are the following: that the start with chart. I mean, this is not an axiom. Sorry. Start with a chart of causally convex open set, which covers M, and then look at Unitel star algebra AO. And this really is the algebra of local observables in any QFT in Minkowski spacetime. Unitel because there is an identity element which is common to all the AOs. So that's important. And star is simply that conjugate of any operator inside this is also in this. So that's these are our algebra of local operators. And then they satisfy these axioms that if O1 is contained in O2, then AO1 is this one. And second is that if O1 is in the causal complement of O2, then AO1, AO2 is 0. And third, that for any element of the Poincare group, A of action of, so I'll write it like this, action of alpha G, action of the group on this algebra is exactly same as, so this is the spacetime covariance. And finally, time slice axiom, which now is an axiom because for a generic interacting field theory, we don't have any proof even in Minkowski spacetime. So, oh, sorry. I should not write here. Okay. So this 3 I should erase also. Thank you. Okay. So then, so this is really the now why are we doing all this? Because this kind of make us understand locality properties of quantum field theory nicely, which in a way that we can ask similar questions when we switch on gravity. So yeah, there is an action of there is a automorphism of Poincare group on this algebra elements, which is such that action is same as if you just translated the set by G. Oh, sorry, you are right. Thanks. That's what you mean, I think, right? Sorry, Ashok, you were saying something.
Number 2, no, there is nothing to replace.
No. So that will completely be part of building AO, right? You have an interacting field theory, then they will satisfy some interacting equations of motion. So we don't have AM to begin with now. We are going opposite now. We are starting with AO, which satisfies all these properties. And these AOs, of course, come depending on a theory, they will change. Yeah.
So you're looking at an interacting scalar field theory?
Right, for example, right.
How do you know it exists?
No. So I think that's what these people would say that, for some, it won't exist as a quantum field theory. But you can do perturbation theory, of course. So I think that I should, in the end, maybe I will mention some references, though. For example, Stephen Hollands and Wald have developed perturbation theory based on Hag-Kastler axioms in Kautz spacetime for phi-4 theory, for example. So you can do the things we do, but maybe at a more abstract level.
Is it the idea that as long as you find a solution to these axioms, you have a quantum field?
Yeah, that's the point. That any quantum field theory in Minkowski spacetime should satisfy. Some people drop time slice axiom. So this one is something that is relaxed sometimes, but none of the other axioms are relaxed. And so finding QFT for them reduces to finding exactly a system of algebras which satisfy this. So AM really is not something that now one worries about directly, in the sense one could now build it based on AOs, but really AOs have become now fundamental object. We don't even have Hilbert space right now, by the way. We just have some operators which are local operators.
You are not actually asking a scalar field, it's not arbitrary field, right?
Yeah, in general, of course, yeah. But I think I will stick to scalar field theory. This for any QFT.
Yeah. So far, nothing that you have said here refers to scalar.
No, only my example was for, of course, scalar. Yeah. No. These axioms are just axioms. Yeah. So the point is that the first thing to start is with algebra of local operators, which are supported inside these causally convex sets. So already, for example, in QED, this restricts the choice of AO. So, because we want gauge invariant operators which are local, so the only thing you can start with is field strength and the current, for example. So, even to do things like QED becomes complicated to build QED as a theory from here becomes complicated. Because, you want to start with operators which are local, and so observables which are local in this sense. And so, you are already restricted even in abelian gauge theories. Yeah, so that is something that is ongoing, I think, in their community, is to include, for example, in principle, we could say that I can have a psi bar Wilson line psi, where both the psi bar and psi are in the O. But initially, this was not allowed because it's too singular for them. But now there's a advancement of refining these algebras to include these kind of operators with Wilson line. But so far, no. Like in the older days, QED for them was really starting with the current and field strength. Yeah.
For example, you have reduced causality and metric converge, but what does time slice axiom actually?
Yeah. So time slice axiom is really about global hyperbolicity. So it is simply telling us that if you give me Cauchy data on a slice, that is enough, and if your equations are hyperbolic, then that's enough to determine the solutions with in the domain of dependence of that Cauchy slice. So that's what time slice axioms is motivated by. For free field theory, it's immediate, but in general, as far as I understand, it's not been proved at this level. So that's why it's an axiom. But it's a perfectly natural axiom. I mean, it's not. Yeah.
So in the Hawk-Cluster axioms, one also usually using these operators as bounded.
No. That's not true. The original Hawk-Cluster axiom is really this. But the bounded operators, as we will see, come when we do representation theory. Yeah. So this is really Hawk-Cluster axioms where we don't start with bounded operators. It's just this.
So bounded, that involves a norm. So here there's no norm.
Yeah.
Is there a topology at least? Can I take limits in my algebra?
No. That's an excellent question, and this is why we will go to when we start studying these quantum field theories, we do not work with this algebra, but we work with, as we will explain, von Neumann algebras which are generated from them, and they are bounded and they have a nice topology, etc. And that's the reason we go to these von Neumann algebras. But we really start here, which are unbounded operators with no good topology or anything. I mean, it's just this. It's really, intuitively built out of monomials of, say, scalars, for example. Like that's.
So the algebra would only include the bosonic operators, or you would just add an anti-commutator?
Yeah, we will add anti-commutator. Yeah, thanks. Yeah, I should have. Yeah. So this is bosonic. I apologize. Yeah, but we can certainly. Yeah, I mean, these axioms would be generalized if you have fermionic fields. Yeah. Oh yeah, because AO will be different. That's the point. So AOs think of AOs as like on-shell quantum operators, locally supported inside O. So they depend on the dynamics, right? They are not Cauchy data or anything. They really depend on the dynamics. No. So that's in the atom of our. We start from AO. So remember, in the free field example, of course, it was here. So we start with this global algebra, which was algebra of all fields which satisfy equations of motion. So now we are going opposite. We are saying that, okay, I start with AOs, which are, for each theory, this AO will be different, but it will be a good theory if and only if these axioms are satisfied. Is that? Yeah. You are asking where 2 went. So 2 has gone inside AO. So AO is built out of some theory, of course. If you start with some Lagrangian and you build your AO. Okay, so this immediately buys us is a couple of interesting things. So far as you see, we don't have a Hilbert space or anything. And so many questions are about this only. So the usual route to go from here to the usual quantum field theory via what is called GNS construction. So I won't go into details of GNS construction. I think which was this covered last week or no, not covered. Okay, are you familiar with GNS construction, or should I review it quickly? Okay, I will just review it. So the basic, let me just quickly review it, and then it will be clear what, for free field theory, it will be immediate what this means. So let's start with some unital star algebra. A. And so the idea is that we want to represent, what is our goal? Our goal is to represent A as some operators on some Hilbert space, H. So to quantize is to find this Hilbert space and action of these operators on this Hilbert space. And this GNS construction is one way to do it. And intuitively it is like start a vacuum and then apply Fock operators, but it's more general because it doesn't assume that we have Poincare invariant vacuum or anything to begin with at least. And so the idea is that consider, okay, I will explain. Positive linear functional on A, by which we mean some function from A to complex numbers, which is such that if you take any element A, if you take any element A in A, then the action of, the evaluation of omega on the square of this element is always positive semi-definite. And it's linear, so for two complex numbers, alpha and beta, this is and so now given this omega, we can immediately construct the Hilbert space on which this A acts as operators, concrete operators. So far A's are some abstract elements, right, which satisfy some algebraic relations, but we can oh, I can write here. We can use this to construct the Hilbert space, and the construction is simply as follows. So look at all elements. Please ask, I'm being a bit schematic, but please ask if something is, I'm saying something wrong. So look at all, let I be all elements in A, which is such that then it turns out that this I is has a nice property that if you consider it is what is called the left ideal. Okay, this is not very important, but just for completeness I am saying it. So what I mean by this is that if B is in I omega, then B dot A, one can check using Cauchy-Schwarz inequality, is also in I omega. And because of this, what happens is that if you take A, you can nicely quotient by this. This is a property of ideals, that because they are preserved under action of any element, you can do a nice unambiguous quotienting of your original algebra with this. And so that let's label these elements of this quotient as some equivalence class A, by which we mean it's A plus I omega. Right, because now basically any elements of I omega has been reduced to 0 inside this quotient. It has been reduced to something trivial. And thanks to this, what we can check that on this quotient is always positive. Because we have kind of removed I, because we have removed all the 0 norm states if you want. And so A star A, thank you, yes. And now, so now the Hilbert space is the following simply. So take Hilbert space to be, it's, take all like, take arbitrary linear combinations of elements of this such that, and this sum can be infinite such that mod alpha n square is convergent. And on this H omega, our algebra acts very nicely, and it acts simply as, I will just delete this. It will act as so So now I can represent my element of the algebra as a hat, and its action on a state B is A dot B. And one can check that this is unambiguous. I mean, one can just work it out and see that it doesn't depend on the representative of this equivalence class. It is. So you see that this was a state in the Hilbert space. So please, I'm saying some garbage. Please stop me. If this is a state in the Hilbert space, and this is also a state in the Hilbert space. And this is the representation of the element A as of the algebra. And so sometimes you will see in the books this is often written as. But it's just our usual quantization. For example, if I take, one can check that if you take usual free field theory, then there is there is a omega which basically corresponds to choosing the usual Fock vacuum. So one can recast our usual QFT on Fock space in terms of the GNS construction. But I hope you get the idea of what this GNS thing is. What is interesting from our perspective is that you can, so one can bypass Hilbert space in some sense. So the reason GNS, I brought up GNS is because you can bypass GNS Hilbert space as follows. So take any element, say, let's say, so let's go back to the free field theory as an example again. And let's go back to our AM. And so what this GNS is obviously doing, it's a positive linear function on any element of the algebra, right? So let's take phi f1 to phi fn, where f1 to fn are some compactly supported functions, and the GNS construction is simply telling you that I can evaluate this function on this element in the algebra. This is in the algebra, right? Because I'm multiplying operators, and so this is this depends on, of course, f1 to fn. So let's write it as some f1 to fn. So so if you specifying omega on the algebra is same as specifying omega on all these products of arbitrary products of these operators inside the algebra. No, this is just correlation function. So so let me just give an example. So for example, in the case of so let's choose an omega as an illustration. That will make it clear. Oh, yes, thanks. Yeah, I did not. So sorry, I deleted it. So AB was omega so now let's give two examples of omega in the case of free field theory. So one is the following. Consider, so these are called quasi-free states. So they already, you see, a slight advantage of doing maybe this bit abstract formulation, that even for free field theory, we put thermal state and Fock vacuum on the same footing in the following sense. So let me generate, let me give you this omega on any possible product of the operators as follows. So let's consider the following omega. Such that plus omega on any arbitrary product is via weak expansion. So I won't write it, but so this is my definition of omega. So I'm giving you one example of omega on the case of the scalar fields, which is such that the 2-point function is this, and any n-point function for even n, for even n. Even n is just from the usual weak expansion, and for odd n it's 0. So, and of course you will recognize that this is our usual free field 2-point function, and then the weak contraction tells us any even endpoint function as a product of 2-point functions. And the other interesting example of omega or a quasi-free state is, sorry, one nomenclature that in algebraic quantum field theory, when people use the word state, they really mean this positive linear function and not the state in the Hilbert space. So those are, it's just sometimes if you read these books, this can be sometimes confusing, but state is really what by state it is meant this omega. So the other choice of omega, for example, which is also completely fixed by the 2-point function, would be, let's say, and again, everything else fixed by the Wick contraction and 0 for odd n. So this is I think the thermal 2-point function. So this is a nice illustration of somehow a little bit of a power of this algebraic approach, that because we start with the algebra of operators and not Hilbert space, we kind of we democratically all the different representations are democratically treated on the same footing, in the sense of you just specify for me positive linear function which evaluates any element of the algebra and gives us a number, right? So you know in general, of course, these omegas are hard to find except these simple ones, the free ones, but even there is just a bit interesting. So any questions so far on this? Yeah. Say that. Yeah, that's a great point. Yeah, in this case, the ideal is trivial.
Is there any example where
That's another good point. Yeah, that's a good point. I mean, I can give you some, maybe we can talk later. I can give you some cooked up examples. I don't offhand immediately remember some physically realistic example of. Okay, yeah, okay, thank you. Yeah, of course, certainly it's true that if for gauge theories, you will have, you will have a problem, because then you will have some zero norm states that you will have to quotient out. But yeah, so thank you. Yeah, so that's one example where you will find non-trivial ideal. Okay, now let me quickly tell you. So just the upshot again is that start with this algebra, and then the full quantum theory then in that case is you give me the algebra of operators. In fact, you could reverse. You could start with this algebra of local operators which satisfy these axioms, and then you specify on if you give me an omega which is a positive linear function on this algebra like these two examples, then I have my quantum field theory, including my Hilbert space and operators and everything. So this is the sort of the abstract idea that now the abstraction of algebraic quantum field theory. Now we can ask what it buys us in some sense, and one remarkable property that comes out is what is called the Riech-Leader property. So I will quickly just summarize that statement. So again, I will restrict to QFT in flat space. And this is really, as I think many of you, of course, know it much better than me, is this is really the entanglement. So entanglement property in some sense, or correlations. So in order to just motivate the basic idea of Riech-Leader property, when you have Minkowski spacetime, I'm just going to first give an immediate. So we start with. So I'm going to give a bare bone argument, because the proof is of course complicated, but just going to give you the main steps. And the first point is what is called a spectrum condition. I will explain. which really effectively means positivity of energy, but that arises out of Poincare covariance. So the fact that the fact that these algebras have to satisfy this property for any causally convex open set implies that we can show that from here that if omega is G invariant, G is the Poincare group, or actually let me just check translation group right now. Omega is translation invariant, by which we simply mean that if I consider omega alpha GA, alpha GB, then that is same as omega AB. So if I give you this GNS function, positive linear functional, which satisfies this property for all translation, then we can immediately deduce the following, that there is a unitary representation of the translation group on our GNS Hilbert space, which of course we know for free field theory in Fock, right? We know that this is just trivially true, but it has an interesting offshoot. So if omega is translation invariant, then the one can show that u hat of G is of the form integral. So G let me write G as, sorry, G is now translation, so it's some vector, so let me call it V. I apologize for the change of notation. So V is just vector, and which generates translations, and then u hat of V can always be written as, and with some measure, and the main point is that this measure, so the spectrum condition says that this measure has support only in forward light cone. So again, this property just follows from the invariance of the omega, that if you started with your these algebra of operators, and if you choose an omega which is translation invariant, then it tells you that translations are unitarily represented. Not only that, the unitary representation of for any translation vector V has support, if you can write it as a kind of a spectral representation as integral over momentum, it has support only on the mass shell and on the forward light cone. So that's the spectrum condition. And because of this, you can check immediately that now the following statement is true, that the following two statements are true. One is that this implies that one can also define u hat over complex generators, where such that zeta should satisfy zeta square and zeta 0. So you can analytically continue your unitaries for translation over from the real translations to complex translations, where the complex vectors have to satisfy this condition, because you can immediately check that this integral will then converge because P satisfies this condition. Okay, so if your if your zeta is also in the forward light cone like V was, then this still is a unitary operator because the integral will not diverge. And because of this, one can use this to simply prove the following property, that so I will not go into proof, it's nicely written in this a beautiful review by so there's a very nice review by and which has this nice summary proof of Risch-Leader property. So I encourage you to see this review. And so there the statement now is the following, that if you now consider um, uh, you know, so take any element in the Hilbert space. So now that we have this GNS Hilbert space H omega, let's consider in this.
Alok, why is P2 positive again?
Say that again.
Why is P2 positive? P2 is just momentum or something, right?
P square. Oh, sorry. This one you mean? Yeah, P square.
So actually, I didn't understand there. Where in the theory did you say which way is future and which way is past?
Yeah, I should. Yeah. So, yeah, this is future for me. So, yeah, I didn't specify it, but my convention is that this is a future light cone.
But I mean, where in the, so that's a theorem?
That's the spectrum condition that comes out of the fact that that omega is translation invariant. Then it will tell us that for any V, your unitary is always written in this form. And if your signature is plus, minus, 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 then this is the spectrum condition.
It doesn't seem like anything in those conditions distinguish between, what you like establish which way you're considering forward. So how does it fall out?
Sorry, which condition? The
How did you break?
Yeah, you're saying where the yeah, that's a good point. So I guess this is true, right? This one will just follow that it has to be. Yeah, it could be either actually, you're right. It could be either, but then whatever that is, then this one will also change.
So there's some choice you made there.
Yeah.
But you didn't have to make that choice, but it's sufficient to make that choice.
Yeah, this I will double check. I don't remember now the details where it comes, but I think right now I don't immediately see where the one side came. You're right. Maybe because the fact that implicitly maybe I assumed some orientation in the Minkowski. That is one possibility, but I have to double check the fact that some time orientation I've assumed in the Minkowski. So my forward time translation and backward I'm distinguishing, but I will check this. Yeah, so consider now, so let me just say one thing, by the way, that before continuing, that here how much time I have? Oh, okay. So let me just say one small thing here, that the in the GNS that I wanted to hide, but maybe I will just say it here, that as we saw that, the giving quantization is simply giving value of this for any element of the algebra. And this really should be thought of as correlation functions in vacuum. So think of this as a definition of the vacuum state. So if you give me an omega, it is you are giving me a vacuum by simply saying that evaluation of omega on any element of the algebra is same as the correlation function of this element in the expectation value of this element in the what we would call a vacuum. So when we have spacetime isometries, then this would really match this. Like for example, if I choose this omega to be the quasi-free state, the first quasi-free state, then this will be the Fock vacuum, as one can actually prove. So this omega is it's usually called cyclic vector, because you can generate the full Hilbert space by acting with full AM on this omega, exactly like in the Fock vacuum, right? All A daggers will generate the Fock space. Vacuum sector? No. Because start with a vacuum, then if you think, all states can be obtained by action of operators on the vacuum, right? Oh, right now, yeah, let's just focus on, that's a very good point. Let's just focus on scalar field, because that's a more complicated situation. There's a whole different story about superselection in this, but let's avoid that for a minute. Because once you have charge sectors, you have infrared issues, and things are very different then. Okay, so now, sorry, so I just wanted to say that this, yeah.
Look at this statement, omega is defined in terms of this vacuum. But where are you going to produce this omega
Yeah, that's a very good point. So we have it's very hard to give, if you give me this algebra and I want to check that there's a positive linear functional, it's very, very difficult. We have few examples only. So one is quasi, these free states, or we have to do perturbation theory. Yeah, so, it's the thing that we do, but we can do it in this framework. Yeah. So I think that there are perturbative schemes people have developed to get omega order by order in perturbation theory from this quasi-free states. We can have more discussion. I mean, recently one of the things that has come out is some new class of omegas, which are called Sorkin-Johnston vacua, which are basically like states, which are like vacuum states localized inside like finite wedges, but they have some pathological properties if you go to the boundary of this wedge. And so interesting states can be constructed which are not our usual vacuum, for example. So maybe we can, maybe if I have time, I will discuss.
You want to use some kind of bootstrap for this omega?
Bootstrap?
To find this omega. I mean, look for omegas by bootstrap.
Yeah. So people do it. That's an excellent point. So there is a. Yeah. No, people do this. You are right. So Stephen Hollands has a program. It's really OPE for quantum field theory from this algebra, which is really bootstrapping in some sense. But it's just operator product expansion for quantum field theory. So sorry, I was saying something. Of the Riech-Leader property. So the Riech-Leader property now simply says the following, that if you start with AO for any O, so you now take this omega, which is the state corresponding to the GNS function, and apply AO. And this generates the full Hilbert space. I mean, there is some convergence property, but if this was true for all elements of AO, then it would imply that psi is 0. So the proof really follows. I unfortunately don't have time, but the proof really follows from existence of this. It's cyclic and separating, but the proof really follows from the existence of these complex translations where zeta is in the forward light cone. So the fact that these unitaries exist, you can use this to immediately prove. It's a few lines proof to show that this is true. It requires some complex analysis, what is called edge of the wedge theorem, but it's really not a very complicated proof once you appreciate this fact about the unitaries. And so this is a remarkable statement, of course, because it's telling you that you could have this psi could be a state anywhere in the Hilbert space, right? I mean, it would not be supported necessarily inside O, but all of states are effectively generated by action of operators which are local. So as far as constructing states go, the algebra of local operators is enough. Like, we don't even have to look at the full algebra. So this point is of course well appreciated, that through entanglement that for that AO generates the full Hilbert space. No. Any of our causally convex open set, what we started with. And so that's the proof really came from the fact that omega is translation invariant, and so that gives us these unitaries. And then the fact that these unitaries can be extended because of the spectrum condition, that is enough to prove. I think Witten also has a nice proof of this in his review.
So if I take infinitesimal space on Eno, and then from that I can generate the entire, I can obtain information of the entire input.
You can generate all the states. You cannot get information, as we will see, but you can generate the full Hilbert space. So any state in the Hilbert space, it's a remarkable result, right? But this result is not you cannot build a starship based on Riech-Leader property because of cluster decomposition. So the fact that, let me explain in a minute what I mean, sir. So it tells you that you have entanglement across arbitrary distances, but of course if you go at large space-like separations, then your correlation factorize, right? So it is not that you can build any, there is a antagonism between Riech-Leader property and cluster decomposition. So usually in perturbation theory, cluster decomposition wins but this property exists. Yes, that's the yeah. So let me just say one thing, that corollary of Riech-Leader property. Yeah.
You can build a star sheet, right? By applying some operator.
It's very hard to build. Okay, I should have not said you cannot build. It's very, very hard to build. Very far away starship will be hard to build.
But you can build.
In principle, yeah. But you need exponentially large number of these operators because of the cluster decomposition, right?
But also you're not if you have to act.
Yeah. This is not. This is absolutely, that's the important point. These are not unitaries, right? Because we didn't even start with unitaries. So these are really unbounded. As Finn was saying, these are unbounded operators that we are working with. Yeah. Yeah.
Suppose you wanted to find an omega which will violate this property, which will not have the Riech-Leader property. What sort of constraints will that take on?
Yeah, if you start with some omega which is not translation invariant, for example, then you won't have. If you just start with GNS omega, which doesn't have translation invariance, then you will not find Riech-Leader property. Right? Because it really comes from the spectrum condition. Yeah. Okay, let me.
Imagine creating some state out of omega, which is not translated.
Say that again? Yeah.
Put some
Yeah, that's true. That is true. Yes.
and declare that is only omega. Right? That's not translation invariant.
Yeah.
You presumably still have the.
No. If your Hilbert space contains an omega, then there is no problem. Then you just have an irreducible representation of your algebra, right? So wherever you start with, you can go back to omega. I'm saying that if you start with your omega which is not irreducible, and so then you will not be able to get Riech-Leader, because the whole point is you should have unitary representation of the translation group with spectrum condition. That's the only requirement. So the way I've actually phrased Riech-Leader also, it very much is dependent on the Minkowski space existence, but there is some work by Sanders on how to generalize Riech-Leader property to globally hyperbolic spacetimes, where of course you don't have translation invariance. So it's not very well understood, but there is some statement that you can generate, if you give me some cyclic state, for example, quantum field theory in de Sitter, then there is some Riech-Leader property that you can find. So, for de Sitter, for free field theory, this was explicitly proved by Ian Morrison. And for general spacetimes, there is some argument by Sanders that they exist, but it's not completely, as far as I understand, settled. So Riech-Leader property is really totally well understood for field theories in Minkowski. Of course, not free field theories, right? We didn't assume anything like free field theory. So it's a generic statement of quantum field theory. Any interacting quantum field theory also. Oh. Yeah, so de Sitter is one example, right? I mean, global de Sitter. So global de Sitter, the Ian Morrison has constructed for free field theory this what we call quasi-free state. Like there's a 2-point function such that it satisfies the corresponding vacuum, satisfies free field Riech-Leader property. And it's the way he proves it is that, of course, because there is no translation invariant, so you have to really go to the tangent space and look at the property of the singularity of the 2-point function in the tangent space, and from there he deduces this idea that this exactly this property. So it's one example of compact space where we know spatially compact. Yeah. Okay. So one interesting, of course, statement about Riech-Leader theorem is that if you consider for any two elements, so suppose A belongs to AO1 and B belongs to AO2, then this can never be written as some omega prime A, omega prime. This cannot be done because, of course, there is a correlation. So Riech-Leader property tells you that you cannot localize, you cannot localize these operators in the sense of expectation value in this. You cannot have a state at this point only in A01, which is restricted only in A01. So given any two operators which are in different causally convex sets, no matter how far O1, O2 are, they can be space-like separated. You can never have the fact that this, for example, expectation value breaks into some expectation value of A in some state and expectation value of B in some state. There's no such exact equality that we can find. Of course, we know that there is a cluster decomposition which is slightly different, which basically tells us that. So this is a corollary of Riesz-Leader property. And we will see that this there is a nice way to there is a nice in some sense opposite side of the story, which is called the split property, which maybe I will not have time today, but in the next lecture we will talk about. But let me just finish by saying that Riesz-Leader property is of course have to be complemented with cluster decomposition, which also has a rigorous proof in actually algebraic quantum field theory in flat space-time, and that basically tells us that if you consider, I'm now writing it schematically, but I hope it's clear what we, so take some causally convex set O and you translate it with a spatial vector, and then you take the limit, then this factorizes into plus corrections which die down at some, I guess it's, sorry, I may be forgetting some factors, but so this is of course cluster decomposition, which also can be proved for interacting field theories in this via this axiom. So this proof is given in, just give a reference in this book called I forgot the title of the book. PCT spin statistics and all that. Yes. So there is a proof of this by this axiomatic quantum field theory in this book. Yeah. So sorry, I could not finish what I wanted to say about flat spacetime quantum field theory, and maybe next time I will start by explaining the absolutely remarkable statement. Let me just summarize in, maybe I can take 2 minutes. Let me just say what the split property is conceptually, and then we discuss it in detail next time, because that will be the key for us when we go to gravitational observables. So the split property is really about the fact that the causality really, when we look at causality, and the statement that if you give me two operators, let's say phi f and phi g is 0 if f is in some f support of f is in O1 and support of g is in causal complement of O1. So this is just obviously telling us that these two operators can be measured simultaneously, but the Riesz-Leader property is telling you that it will be hard to prepare states even if you have two regions O1 and O2 which are space-like separated, and so any observable here can be measured simultaneously with this observable. But because there is entanglement, is there any way that I can prepare a state in a lab which is in O1, localized in O1, without at all affecting the environment, the universe of O2? So the idea is that is there any way to prepare a subsystem localized in O1, and the answer to this question is yes. Of course, that's why we are talking about it, and that is that is what is called the split property. And so we will see that this is as far as we can go without talking about von Neumann algebra. And so now we will go to the more refined structure of these algebras, which next time, and that will, those are the ones that will tell us that there is this, there is a way that we could divide our quantum field theory into subsystems, which, where not only measurement can be independent, but even preparation of state can be independent. So that, and then that will basically take us to gravity, as whether we can do such things in gravity when we have gravity. Yeah, so the one is, I will write the, I think this Witten has a review which is very good, of course, but I think there are many beautiful older reviews. So let me just write some of them here. So there is, of course, a book by Haag which is very famous, Local Quantum Physics. So maybe that should be the first reference. And then there is on Klaus Friedenhagen's webpage, there are lecture notes on algebraic quantum field theory. They are very short, and they are just, I think, 30 pages or so. Intro to AQFT. And then this beautiful review by what I mentioned earlier, Cassia and Fuster. It's called Intro to Algebraic Quantum Field, Introduction to it. And then Witten's, recent Witten's review is also really beautiful. Witten's review. Actually, there are many. If you go to even this one, you can find reference to many other reviews. Okay, I'll stop here.
Any questions?
No, it will not violate each leader. No. Yeah. We will have to go beyond. So the reach leader is, as he mentioned about these unbounded operators, right? The split property will be slightly different in the sense that you will see it will not violate reach leader. So we have reach leader, and we have a way to define separate subsystems. They will have entanglement, but we can prepare states which are local in a lab.
Suppose I give you over and I demand this sort of a state. Can you give me the small omega, that state?
Yeah, absolutely. So the way the split property overcomes reach leader is by giving so when you prepare the state which are localized, they are obtained in terms of these omegas which are really weird, as you will see. They are a bit pathological, but they are like very local. This omega is global, right? Think of it as a vacuum. Vacuum is not local, right? If you want to prepare a state somehow very localized, you have to do something kind of pathological from the perspective of the vacuum. And split property tells you that such things can be done, they exist. So what is beautiful about split property is that unlike reach leader, whose clean proof is in flat spacetime, split property proof is in any globally hyperbolic spacetime. It doesn't rely on flat spacetime because it doesn't rely on spectrum condition or anything.
Any further questions? If not, let's thank Alok again.
Thank you.